Okay, so this question today is a follow-up from some of the information we learned about our sine and cosine functions yesterday. So if you're watching this as a lesson video right now, take a second and pause it and see if you can fill in this information about our function. Everyone in class has already had some time to do this, so we'll take it up. Can somebody tell us what our amplitude is? Elise. 4, yes. We want to take the absolute value of the a value, and we will get 4. Sam, do you want to do period?
Half. Oh yeah, I totally forgot about that.
Yeah, so we'll take 360 and divide it by the k value to account for any horizontal stretch or compression that has happened, and you should get 720. Okay, how about phase shift? Can someone help us out with that? Go back to Elise. Good. That comes from our d value right here. So we remember that when it looks negative, it's actually positive, and it's shifting right. Vertical shift, Ivana.
Up 4, yes.
Up 4, very good. Lovely. And then how about our max and our min? We talked about kind of like a picture of what can help us get max and min. So what helps us with that? Olivia? Yep, so what are we counting up from and to? We're counting up 4 from 4, that's right. So we use our C value, which is 4, and we're going to count up and down the amplitude from that. So we're going to count up 4 units from 4, which gives us a max of 8. And then we'll count down 4 units from 4, which gives us 0. Did someone say 1? Okay. The little formulas that we talked about yesterday, I can find max by doing C plus the amplitude, and I can find min by doing C minus that amplitude. That's essentially what we're doing when we count up and down the amplitude. We're adding it and subtracting it. Okay, so that's kind of our crash course in what we talked about yesterday. Sebastian, can you grab that back door for us there? Thank you. Any questions on this? Okay, so just to remind you guys, we never talk about amplitude and period as negative values. Can someone tell us why we don't want amplitude and period to be negative? Nobody knows? Ivana? Yeah. Yeah, we're talking about a measurement of like height and length of the graph, right? Amplitude is half the height of the graph, and the period is the horizontal length of a cycle. And I can't talk about lengths and like actual measurements as if they're negatives. That doesn't make sense. So we use the positive value because we're just counting like number of units. Okay? Cool. All right. Today is essentially just going to be a bit of a review, refresher on transformations. We're going to be using 2 functions that were introduced to you yesterday, which are the sine function and the cosine function. I asked you guys to circle some points on your table of values yesterday, and those are going to actually be used as our key points. And if you weren't here yesterday and you haven't had a chance to catch up yet, it's really easy to remember. We choose the x values as those values from last chapter, which were on the separating quadrants of our cast grid. So it was like 0, 90, 180, 270, and 360. And if I can just remember that one single thing, that's what I'm going to use for sine and cosine. I should be able to get my y's because I have the equation that gives me the y's if I have the x's. So all I need to do is take these angles and plug them in to sine and cosine with my calculator in degree mode. So if I start plugging each of these in, I'm going to get 0, 0, 91, 180, 0, 270, -1, and 360, 0. Okay, and then same thing for cosine. We'll be plugging each of these in, and we'll get 0, 1, 90, 0, 180, negative 1, 270, 0, and 361. So these are going to be the two sets of key points that we use for our sine and cosine functions. It will obviously depend on what the parent function is, so that I can choose which set I'm going to use. Okay, so the sine and cosine points are very similar, but you'll notice that they're kind of shifted versions of one another. Some of them are zeros when others are ones. So we just want to be mindful about choosing the right set of points. Okay, so we're going to do some transformations with these. Am I okay to flip? Okay, so we're going to work on doing transformations given the function y equals 2 sine x plus 1. So we're going to start with y equals sine x. So these are our points that we'll start with. It's always good to rewrite them out. You kind of commit them to memory that way. Although you don't have to memorize them necessarily. So that's what we're going to do. And then just to remind you guys, this is how we set up our tops of our transformation equations. We do reciprocal of k times x, switch the sign of d, and then a and c will go into our equation exactly as we see them in the equation. So out of a, k, d, and c, what values do we have in our sine equation here? Yeah, how did you know that this was a c and not a d? Elise? Yeah, so if this were in brackets, that's a d. If it's not, it's a c. So I actually have no changes to the x's here, right? Because if we only have a and c, those are both changes to the y. So I can actually just recopy out the x's. 0, 90, 180, 270, 360. Okay, for our y's, we're going to do ay, which is 2y, plus our c value, so plus 1. And then I'm going to take each of these y values on the left-hand side here, and I will plug them in and multiply them by 2 and add 1. So 0 times 2 plus 1 is 1. And you'll notice here, guys, I actually have 3 zeros. Is it necessary for me to calculate it every single time? So we can just actually put those in for all of the zeros. Save ourselves some work there. And then we'll plug in 1, so it'll be 2 times 1 plus 1 to give us 3. And then we'll plug in negative 1. So negative 1 times 2 is negative 2, plus 1 is negative 1. Okay, try to keep your points in line as best you can so you can see which x matches up properly with which y. All right, I'm going to go to 2 pages here so that we can see our points as we graph. So we are going to graph the parent function and the transformed function, and our goal for our transformations for today is going to be to fill the space between 0 and 360. So we'll start with sine. Sine is at the point, do this one in blue, 0, 0, 90, 1, 180, 0, 270, negative 1, and 360, 0. Okay, and if you remember back from yesterday, we graphed some of the in-between points as well, and we saw that these are actually more like curves rather than like straight zigzags, so we want to make sure we do nice smooth curves rather than like sharp edges on these guys. Okay, and this is just our parent function here.
Wait, I'm confused. I thought 90 was 3. Oh.
I'm graphing this one right now.
I got so confused. I was like, mine looks right.
Okay, and then we're going to go and graph our transformed function. This one I'm going to do in red. And then again, nice smooth curves here as best you can. And we'll just label it up here. You'll have to practice your curves there, Karen. Okay, so we're going to do a little comparison of some of the properties here between our parent function and see how our transform function has changed. We can do these observations with the equations, and we can also observe on the graph how some of these things have changed as well. So yesterday we took some time to discuss the properties of sine and cosine after we graphed the basic functions. Does anyone remember what we found the amplitude of the regular sine function to be? What was that? 1, yeah. So the entire graph goes from -1 to 1, so half the height of the graph is just 1. The period, how long does one cycle of sine take? Yep, 360, very good. And if we look up at our graph here, we can see that only one cycle fits between 0 and 360. We can measure a cycle when we're talking about sine and cosine as one full mountain and one full valley. We could measure it from a max to a max. It just depends what points we have. But we can see here there's one full mountain and one full valley, and the pattern doesn't start repeating at all. So this is one full cycle of sine right here. So between 0 and 360, one cycle fits. Okay, what is the amplitude of our new graph? 3? 2? Yep, so we can actually see this from the a value in the equation that tells us the amplitude. Or I can take a look at my points here. So my minimum goes from -1 up to the maximum of 3. So the whole graph is 4 units. So half of that is the amplitude, which is 2. So I can observe graphically, or I can observe the equation. Okay, have we changed the stretch and compression horizontally at all? Have we changed the length of the period?
No.
That's actually the same. Yeah, the k value hasn't changed. So the period is still 360, and one cycle fits between 0 and 360. Okay, so the k value, that stretch or compression factor, horizontally is going to affect the length of the cycle and subsequently the period. The amplitude, that's affected by our a value, stretch and compression. Any questions on this one? Okay, can I flip to the next page? All right, next one. Parent function is looking like cosx. So we're going to start with our cosx points. And we'll see if we can set up the tops of our equations here. Someone want to help us out with the x side for this one? Ivana?
1/3 x
Mm-hmm.
plus 3.
Great. So reciprocal of k and switch the sign of d. Very good. I can say 1/3 x, or I can say x over 3, same thing. Okay, does someone want to help us out with the y side here? Karen.
-1.5y plus 0.5.
Awesome. Okay, so we're gonna take all of our x's, third them, and add 30. So for the first one, we get 30. Second one, I'm getting 30 plus 30 when I plug in 90, which gives me 60. And then the next one, we're getting 60 plus 30, which is 90. So just plugging each of these in, and you should start to see, because my original parent function points are all going up by 90s, the x coordinates, you should actually see a pattern emerging within your new x coordinates. They should all be going up by a common value. So what are the x values changing by here? Yeah, so I could probably not I probably don't need to plug in all the rest of the points. I can just continue the pattern, right? So the next point would be 120, and then the next one will be 150, just going up by 30s. Okay, the y coordinates are a little bit different. The y coordinates have a specific pattern to them, but once we do another cycle of that, the y coordinates will repeat in the same order. So we're going to take each of these y coordinates and plug them in and multiply by 1.5, add 0.5. So I think for this one we get -1 for both of the 1's. And then when I plug in 0 here, we get 0.5 for both of the 0's. And then when we plug in -1, this becomes positive, and we add 0.5 to it, giving us 2.
Do we have to always graph the parent function?
So usually what I ask you to do is graph one cycle of the parent function and 2 cycles of the transformed. Okay, so let's graph cosine to start. I'm just going to graph this one in black. Okay, so there's our cosine function. And then we'll start graphing the transform function. And goals for all of this are to fill from 0 to 360 for the purposes of this lesson. So we're going to start with this cycle that we have here, and then I'm going to show you guys how to extend this pattern as we move forward. Okay, so there's our first cycle. All right, so when we go to extend our pattern, it's good for us to know what the x's are changing by, because that's how I'm going to extend my cycle as well. So every 30 degrees, the y's will follow this pattern. They'll go -1, 0.5, 2, 0.5, -1, 0.5, 2, 0.5, -1, and then again and again and again. Okay? What I like to do visually is I'll keep my fingers on both of these bottom points right here, and as I move toward the right, my fingers must be doing the same thing. So as I move toward the right from 30, my finger is going up to 0.5 at 60. So the same thing will be happening as I move from 150 to the next tick, the next 30 degrees here, which will be at 180. So 180 should also be at 0.5. Does that make sense? So we're just going to follow our fingers along here, and we'll make sure that they're doing the same thing as we track our new part of the function, okay? So our job is just to continue the pattern, okay? So there doesn't even really have to be much math involved in this. All I have to do is just keep the pattern going, okay? So my next point is going to be up at 0.5. So I'm tracing, we're doing the same part right here of that next cycle. And then I'm going up to 90. So in my next 30 degrees, I'm going to be going up to 210 at 2. So there's the second part. Okay, and then we're going down, back down to 0.5. So I'm going to do the same thing here. So at 240, we're going back down to 0.5. Okay, and then back down to -1 at the next 30-degree mark. Okay, so back down to -1. Okay, we're going to repeat and fill. So if I'm going backwards, if I want to fill at 0, if I'm going backwards, I'm going to go backwards up to 0.5 here. So at 0, I'm going to be at 0.5, just filling in this little space here. So again, it should look like I've essentially copied and pasted that pattern there. And it should always go mountain, valley, mountain, valley. Okay, where am I going to be at if I go forward to 300 here?
0.5.
Yep, 0.5. And then at 330?
2.
Up to 2. Good. So you guys kind of get the hang of it, right?
Yeah.
And then back down to 0.5. Awesome. So that is fitting perfectly between 0 and 360. And then we'll just label it with its equation. Okay? So this is the only added thing with transformations of sinusoidal functions, like the sine and cosine functions. We're just working to be able to extend our graph into like a second cycle or a third cycle. Okay, so let's look at some of the changes between our cosine graph and our sine graph. So cosine actually has the exact same properties as sine does. So the amplitude, the period, and number of cycles that fit between 0 and 360 are the same. So amplitude is 1, period is 360. And between 0 and 360, 1 cycle fits. Okay, how have things changed for our transformed graph? What's our new amplitude?
1.5.
Yep, so we can see that with the A value here. We can also see with our graph here, it is 3 units from -1 to 2. And when I cut that in half, I get 1.5. So amplitude is 1.5. How has the period changed? How long is one cycle?
120.
Ooh, I have 150 and 120. So this is one cycle right here. It goes from 0. That's one full cycle. That takes 120 degrees. So, or you can also calculate it doing 360 over 3.
That was my mental math.
Very good. Okay, and if you guys count here, how many cycles are we able to fit between 0 and 360? There's 1. Here's another one. So that's 2 cycles right there. Yep, we can fit 3. What does this have to do with our equation?
It's the K.
It's the K. So the K value actually tells us how many cycles fit between 0 and 360. I know.
I'm really tired.
So far, so good? Okay. You guys are going to start and see if you can set up your tops of your transformation equations for our next one and see if you can get your points. We'll start with that. So I'll give you a couple of minutes to get a head start on that.
That's our homework, right? Yeah.
So I have written out the parent function key points for us, and this is what the tops of your transformations should have looked like. Can somebody tell us who's finished the x's? Tony, did you get the x calculations? Yeah, do you want to list them off for me?
For 1 over, negative 1 over 4x plus 60.
Yep, and then did you do these calculations here? Okay, do you want to tell me? 60, yep.
37.5.
Yep,
50. Negative 7.5.
great.
Wait,
And the
50
last one?
or
Negative 15.
Great.
50.
Awesome. And then I think the y's are pretty easy to calculate. It's 2, 2, and 2, and then 3 and 1.
The graph is pretty savage.
Okay, so we're going to try to fill the whole thing between 0 and 360. Okay, couple conversations happening. Let's just focus in up here. We're almost done for the day. So this one, it would be helpful for us if we recognize what our x's are changing by. So did anybody figure out what this value is that the x's are changing by?
I can figure that out. 22.5.
Yeah, it's a difference of 22.5. So if I'm going in the backwards direction, I'm subtracting 22.5, but if I want to go forward toward 360, I want to add 22.5 to go forward to that. So I'm going to show you guys, these aren't perfect numbers right here. These aren't great because they're not on like exact x values. They're on some decimals. So I'll just show you guys how I usually extend these graphs, and it makes it a little bit easier than having to do like every single calculation of like every single x value, which you can do if you want. But I think that this way is a little bit easier. So let's just start with graphing our parent function quickly, if you haven't gotten to that yet.
Of course we have.
How could I have ever doubted?
Honest. So
Okay, and you'll graph your first cycle as usual. So 60, yeah, it's kind of a problem, right? 37.5 is about a quarter of the way between 30 and 60, so it's going to be like, about like right here. And then 15 is exactly halfway between 0 and 30, so that should be at the halfway point. And then we've got negative 7.5, which is, again, it's about a quarter of the way between negative 30 and 0. So it's about like right here-ish. And then our last point was negative 32. Okay, so there's our first cycle. So I just want to kind of show you guys. Everyone look up here just for 1 second, so that I can show you guys kind of what I do. I actually don't look at the numbers at all. I just look at the spaces of where these ticks end up falling. Is this negative 7? Oh yeah, it is negative. Okay, so I actually just look at the spaces here. So if I want to extend my cycle from here, oh, meant to be on the pen tool. If I want to extend my cycle from here moving forward, I'm actually going to do the same thing over here. And I'm actually just looking at this spacing right here between this like point and the next full point, which is here. So I'm noticing that this particular spacing is about a quarter of the way in between these two ticks. So my next one, when I go down to the value 1, it's going to be about a quarter of the way, or 3/4 of the way, just before I get to this tick. So you guys see how I'm just trying to make sure that the spacing here is the same? Okay, again, if you add 22.5 to 60, you'll also get this next point. Like you're gonna get 82.5, and then you're gonna just approximate it. Okay, my next one, as I go up to this next point here, that next point is actually halfway between 0 and 30. So my next point over here, when I go up to 1, is gonna be halfway exactly between these 2 points. And then we're gonna go up. Okay, so again, I'm not arbitrarily placing these points. I'm making sure that all the spacing is exactly the same. So like this spacing is the same as this spacing around here. Okay, and then where does the next one go? The next one goes just past the next tick. So up at 3, I'm going just past the next little tick there and extending my cycle. And then when I finish off this cycle, it's actually right directly on the next point. So it's going to be right directly on the point 150 there. Okay, so a little faster this time. We're going to keep that pattern going. This one is just before the tick. This one's halfway between. This one is just after. And then the next one is right on. Okay, so just keeping that spacing consistent. Okay, and then one more time to fill it out. Just before, halfway, just after, and exactly on. Okay, and if I really want to fill up to 360, I'm going to be I'll show this point right here. This was bad. I'll show this point right here and how it kind of goes, heads back up from there. Not too bad. Okay, so just as a little self-check here, you should have points on 60, 150, 240, and 330 by the time you've extended this cycle. Those are the ones that are on the exact x value points. The last thing is just to describe the changes of what's happened with our graph. So let's take a look at that. So as we said before, the amplitude of sine, the regular sine graph was 1, period is 360. And one cycle fits between. Our new graph, what's the amplitude of our new graph? Still 1. A value is 1. Period? Yeah. So we actually can do 360 over absolute value of k, which is 4, which actually gives us 90 degrees. We can actually observe this on our graph as well. If I look at from 60 to 150, that's probably the easiest way that I can see how long my cycle is. Between 60 to 150 is 90. Okay, and then how many cycles would fit between 0 and 360? 4, yep. Does the number of cycles that fit between 0 and 360 always have to be a full cycle?
Yes.
Does the k value always have to be like a whole k value?
No, it could be like 3.5.
Yeah, it could be anything, right? It could be a half, it could be, yeah. So it's not necessarily a full number of cycles that will fit.
Well, this isn't a
Well,
full
ours was
cycle.
full.
So this one actually, like if we track from this point right here,
Yeah, it's just, that's why I was saying that.
yeah, so if we track from this point, you'll see that these points are the same, right? It starts and ends at the exact same point here.
That's awkward.
It's just not on an exact cross section, so it's a little bit harder to see.
Oh.
Okay.